All right, greetings, chemistry. This is the second podcast in Chapter 20, and what we're going to be talking about today is free energy and spontaneity. So we're going to continue this idea of spontaneous processes, spontaneous reactions, and we're going to show you today how you can figure out mathematically whether spontaneous or whether a process will be spontaneous or not. So let's just review really quick. Spontaneity, as defined yesterday, what it is. A reaction or a chemical process is spontaneous if it happens by itself, without provocation. Okay, it has a tendency naturally to occur. If you're thinking in equilibrium terms, that means that that process is going to be product favored. So it's going to favor formation of products that have a high value of K, which we'll talk about here later in the podcast. Okay, the things we said yesterday lead to something being spontaneous is if the process is exothermic. We knew this back from Chapter 6, that processes that release energy have a tendency to occur. And so what that means is that delta H, if you were to look at delta H, the change in enthalpy for that process, the change in enthalpy will have a negative sign. So delta H is negative, this is an exothermic process and has a tendency to occur. And of course, the reverse is also true. If delta H has got a positive sign, then the process is endothermic and has a tendency not to occur, generally speaking. Okay, the other thing that contributes to whether or not something is spontaneous is this whole idea of entropy, okay, or the disorder of the system. Now, we said that one thing that favors spontaneity, or favors the forward process, is if the entropy for the process increases, or in other words, that delta S, the change in entropy, has a positive sign. So if delta S is positive, that means there's more disorder, okay, or that things are spreading out, so energy and matter are being dispersed during the process. And if delta S is negative, well, that means that at the end of the process, there's less disorder. And we said yesterday that the circumstance that favors the process occurring is that the entropy is going up, so delta S is positive. So these two things, delta H being negative and delta S being positive, contribute to things being spontaneous. We know that. But what if you have something like, if we're considering a process like the dissolution of sodium chloride? Like we were talking about yesterday, sodium chloride in its native state is a highly ordered crystal. And so if we dissolve sodium chloride in water, this is going to dissociate. It's going to give us sodium ions and chloride ions dispersed in the solution. When that happens, all the order of the crystal breaks down, and delta S is going to be positive. Okay, so there's going to be much more disorder at the end of the process than at the beginning, so delta S is positive. But delta H, the change in enthalpy, is also positive for this process. It's endothermic. Now, we said yesterday that if it's endothermic, that makes it not want to happen. But if delta S is positive, that makes it want to happen. So we have these two kind of conflicting things here. Well, how do we know whether or not it's spontaneous or not? What we have to look at is this last thing here, this last thermochemical property called the change in free energy, or delta G. So the symbol is G because we're going to look at the change in something called Gibbs free energy. And it's called Gibbs free energy in honor of the person who developed the function named Gibbs. So if you discover something amazing in chemistry, it will be named after you. There we go. So what is Gibbs free energy, or what is free energy, and how do we find it? So free energy is the energy that is available to do work. Okay? That is what free energy is. It's not energy that you don't have to pay for. It is energy that can be used to do work. Now, we know, one thing we know is that a process is spontaneous if the free energy decreases. Or in other words, the sign of the free energy change, delta G, is negative. If delta G, the change in free energy, is negative, that means that the process is going to be spontaneous. If delta G is positive, the process is non-spontaneous. So overall, this is how we're going to determine whether or not something has a tendency to occur on its own. And there's two ways we can calculate these, two equations that you have to know and carry with you and memorize. I don't tell you to memorize very many things, but these you want to know because they're some of the most important things in all of chemistry. If you know the free energy change for a process, you can do a lot of things, as we're going to see. So equation number one looks like this. One way you calculate delta G is like this. Delta G is equal to delta H, the change in enthalpy, minus T times delta S. Okay, so you can see that delta H, the change in enthalpy, is part of this, and so is delta S. So both these things we talked about factor into the free energy equation. The other way you can calculate delta G is just like when we were talking about thermodynamics before, and we showed you how to use heats of formation. You can also measure a free energy of formation, which is symbolized with a G and then a lowercase f here that stands for formation. If you look at the sum, okay, so we take the sum of the free energy of formation of the products in a chemical process, and we subtract from that the sum of the free energy of formation of the reactants, we also can find the change in free energy for that process. These are the two ways you can calculate Gibbs free energy. Let's do an example really quick, just to show you how to use the information. So, here's the example. It's on your notes, Kelvin. We're going to calculate delta H, delta S, and delta G for the formation of methane at 298 Kelvin according to the equation that is right here. So we're going to take graphite, which is the most thermodynamically stable, naturally occurring form of carbon, plus 2 hydrogen gas molecules gives you methane right there, CH4. And we're going to answer this question, is the reaction spontaneous, or does it have a tendency to occur without provocation? And again, guys, what these degree symbols mean is that means standard conditions. So 25 degrees Celsius and 1 bar of pressure. Okay. Now, to figure out these things, okay, delta H, delta S, and delta G, well, we don't have any information. So what we're going to do is we're going to look in Appendix K, and we're going to find what is the, we're going to find delta H using heat formation, and we're going to find delta S using standard molar entropies. So let's do that. To find delta H, okay, the standard heat change for the reaction is going to be the sum of delta H, the heat of formations of the products, minus the sum of the heats of formation of the reactants. Okay? If you look in Appendix K, we can find that for the product here, this reaction is methane, and so the heat of formation of methane is negative 74.8 kilojoules per mole. Okay? And now we're going to subtract from that the sum of the heats of the formations of the reactants. Well, it shouldn't surprise you that if we look at the heat of formation of graphite, it is 0 by definition, because that's the most stable form of the element carbon. If you look at the heat of formation of hydrogen, that is also 0. So these two things together, this whole term here is going to end up being 0, and so delta H for that whole process is negative 74.8 kilojoules per mole. There we go, we'll circle that, okay. Now let's calculate delta S. Delta S, okay, the standard entropy change for the process, we're going to calculate the same way. It's the sum of, the sum of the standard molar entropies of the products minus the sum of the standard molar entropies of the reactants. Okay? If we go through and we calculate that, okay, if we look in Appendix K, we can see that the standard molar entropy of whatever it is, methane, is 186.3 joules per mole Kelvin. Okay? And we're going to subtract the sum of the standard molar entropy of the reactants. Okay, so we have 1 carbon here. Okay, and if you look at the standard molar entropy of graphite, it is 5.7 joules per mole Kelvin. And plus, okay, and we look over here, we have 2 hydrogen, 2 times the standard molar entropy of H2, which is 130.7 joules over mole dot Kelvin. Okay, if we go through and we calculate this whole thing, we get that delta S, the change in entropy, is going to be negative 80.8 joules per mole dot Kelvin. Now, if you look at these two things here, the entropy term and the enthalpy term, you'll notice that the units are different. In the enthalpy term, it's in kilojoules per mole, whereas in entropy here, the unit of energy is joules. Okay, so you have to convert these to a common unit. The easiest way, I think, is to convert entropy here into kilojoules. So we're just going to call this, if we divide here by 1,000, it's going to be negative 0.0808 kilojoules per mole dot Kelvin. Okay, if we now calculate delta G for this process, okay, delta G is going to be equal to delta H minus the temperature times delta S. Now we just calculated delta S, we just calculated delta H, so we can just plug these things in here. The temperature is 298 Kelvin, so if we go through and we calculate that, we see that delta G is going to be equal to negative 50.7 kilojoules per mole. We wanted to find right there. So that is the standard free energy change for that reaction. We can see that the sign here, guys, is negative, so if I ask you, is the reaction spontaneous, you will tell me, well, yes, it is, because the free energy of the system is decreasing over the course of this reaction. Okay, so the reaction is spontaneous, but at 29 degrees, or 25 degrees Celsius, right, or 298 Kelvin, is this reaction very fast? We see that it has a tendency to occur. It is spontaneous, but don't confuse this term spontaneous and the idea that it has a tendency to happen by itself with the idea of it being fast. This reaction at room temperature is extremely slow, in fact. Even though it is favorable thermodynamically, it has a tendency to occur, it does not necessarily happen quickly. So do not confuse kinetics and thermodynamics. Okay, let's look at one more. We'll do more application. Okay, we're going to do a second example here. Well, just for the sake of time, actually, we'll just calculate delta G. We'll ignore this delta H and delta S. And we're going to do this in a different way. We're going to utilize this second equation. We're going to figure out delta G for the combustion of methane. But we're going to use our second equation, which is delta G, the standard free energy change, is equal to the sum of the standard free energies of formation of the products minus the sum of the free energies of formation of the reacts. Oop. Okay, awesome. Okay, the first thing we have to know is we have to know what is the balance equation for the combustion of methane. Well, if we think about methane, guys, the state is it is a gas. Okay, plus oxygen, this is the combustion reaction. Okay, that is a gas, and it's going to make here carbon dioxide. The products of combustion are always going to be carbon dioxide here and water, and then it just remains to balance the equation. But your question you might ask, well, Mr. Harper, what state is water in? If this is a gas-phase combustion here, this is going to be initially a gas. The state matters. If you look, delta G, okay, or not delta G, but the free energy formation in Appendix K is different depending on what state that's in. So be specific, be careful with your states. Okay, to balance this equation, we have to put a 2 here in front of the oxygen and a 2 there in front of the water, and now everything is balanced. Let's calculate delta G. Okay, so the product here, we have carbon dioxide and we have water. If we look at the free energy of formation of these things, for carbon dioxide, it is negative 394.359 kilojoules per mole. Okay, and then we have 2 water molecules, so we're going to put 2 times the free energy formation of water, which is negative 228.572 kilojoules per mole. Okay, and then we'll close that bracket off. There's the products. Okay, this subtracting the sum of the free energy formations of the reactants. Okay, if we look at the reactants here, the free energy formation of methane, well, we just calculated that. That's negative 50.7 kilojoules per mole. Okay, and then plus the free energy formation of oxygen. Now, if you look in the back in Appendix K, you'll see the free energy formation of oxygen is absolutely nothing because it is an element in its native state. Okay, and the free energy formation of any element in its native state is also, by definition, going to be 0 all the time. Okay, so if we go through now and we calculate this, we see that delta G for this process is going to be negative 800.783 kilojoules per mole. Okay, and again, guys, this is another example of a spontaneous reaction because delta G is negative. That does not mean, though, it's a spontaneous reaction, has a tendency to occur. That does not mean it is going to be fast. So we can say that, yes, this is spontaneous. Okay. So to summarize, signs and the meanings, delta G. Okay, what does delta G mean? Delta G means, it gives free energy, the change it gives free energy is going to tell you whether or not a reaction is spontaneous. So if we have a case that for a particular process that delta H is negative, so we're looking at an exothermic process. If that process also has a positive sign in the entropy, okay, we look here at the equation for it gives free energy delta G, okay, delta G is equal to delta H minus T times, okay, pen tablets, times delta, well, imagine that's a delta, times delta S. Okay, we can see that if delta H is negative and delta S is positive, then this whole term is going to be negative right here. The T delta S term is going to be negative, and so overall delta G is going to be negative. So if you have a process that is both exothermic and delta S is positive for that process, it is spontaneous all the time. Yes, because delta G is always going to be negative, and this is going to be always spontaneous. Okay, always spontaneous. If you have the case, though, where delta H is positive, okay, so it's endothermic, we know that does not favor spontaneity. And we have that delta S is negative. So both the delta H term is positive, and the T delta S term, because negative T times negative delta S is going to be positive. These are both positive, means delta G is always going to be positive under these circumstances, and it is never going to be spontaneous. Okay? So these two things are unfavorable, positive delta H and negative delta S. These things do not favor spontaneity. So under these conditions, it will never be spontaneous. Now, what if you have these cases? Okay, so say, for example, you're looking at an exothermic process. So the sign of delta H is negative, and the sign of delta S is negative. Can that process be spontaneous? Well, yes, it can. It depends. Delta G can be either negative or it can be positive. And it might be spontaneous. Maybe it's spontaneous. Okay, sometimes it is. It's going to be spontaneous at low temperature. Okay, so here, let's look at the equation again, guys. If delta H is negative, okay, that favors spontaneity. That's going to make delta G, part of the equation here is negative. Basically, in order for the process overall to be spontaneous, the delta H has got to be bigger than the T delta S term is. Okay, so at low temperatures, the T delta S term is going to be small, and that process is going to be spontaneous. Okay, so it's going to be spontaneous at low temperature. If you have a process that's like this, we say that this is enthalpy driven. Okay, it is enthalpy driven. The thing that makes it want to be spontaneous or makes the reaction want to happen is the exothermicity of it. It is the fact that it releases energy. So the enthalpy part of the equation is what's driving the process. Okay, the last case is, well, if we're looking at an endothermic process. We know some endothermic processes are spontaneous, like the dissolution of sodium chloride. Well, this can be spontaneous only if delta S is also positive. Okay, so if delta S is positive, okay, delta G can be negative or it can be positive. It depends. And these reactions are sometimes spontaneous, but in order for it to be spontaneous, it has to have a negative delta G. So the circumstance under which it's going to have a negative delta G is if you have a high temperature. Okay? At a high temperature, the T delta S term right here becomes big, and this overcomes basically the positive enthalpy change. And so we say that this is an entropy-driven process. Okay, it's one that occurs because of the increase in the disorder of the systems. That's what drives the process right there. That's what drives it to happen. Okay, so it's the kind of the motivating factor. Okay, so just kind of keep these in mind. Be able to qualitatively describe what makes delta G negative and understand these factors. All right, guys, let's look at one special case here. Okay, so we know that something's spontaneous, delta G is negative. We know it's non-spontaneous, delta G is positive. But what if you have delta G equal to 0? If delta G is equal to 0, the system is at equilibrium, but it's a special type of equilibrium. Okay, it's one where neither the forward nor the reverse process is favored. They're both happening in exactly, the position of equilibrium is right smack dab in the middle. Okay, an important application of this is boiling points. Okay, so if delta G is equal to 0, okay, so here's our equation: delta G to delta H minus T delta S. Well, if delta G is 0, that means that 0 is equal to delta H minus T delta S. And we can rearrange this further to say that delta H then, at that point, at this particular circumstance, is equal to T times delta S. Okay? So let's consider how we could apply this information. The question I'm asking here in this example is, what is the boiling point of a solution where the heat of vaporization is 23.5 kilojoules per mole, and, oh wait, okay, let's go to the next slide, or this written bigger over there. Okay, there's a slight error in your notes, Colin. That's the reason we did that. So what is the boiling point of a solution where the heat of vaporization is 23.5 kilojoules per mole, and delta S is 34.5 joules per mole times Kelvin? Okay, 34.5 joules per mole Kelvin. So this is an endothermic process. Again, vaporizing is endothermic. So let's think about what's going on. Okay. Imagine, if you will, that we have a flask, and that flask contains a liquid. If you have a liquid at its boiling point, we know that we have liquid particles. Some of these are going to be going into the gas phase at any point in time. And you also are going to have the gas phase molecules going back down into the liquid phase. These two processes are going to be happening at the same rate. So we have a case where this process is at equilibrium, and both things are happening at the same time. At this point, at the boiling point of a liquid, okay, so a boiling point, remember, is a temperature in Kelvin, okay, at the boiling point, these two things are happening at the same process, or at the same rate, so we're at equilibrium. We're going to find the boiling point. The boiling point is the temperature. So let's write down the equation. We saw that if delta G is 0, delta H is equal to T times delta S. If you want to solve here for the boiling point, get the temperature by itself. The temperature is going to be delta H divided by delta S. Okay, let's plug in some numbers here. So delta H is 23.5 kilojoules per mole. Delta S, we see, is 34.5 joules per mole Kelvin. We have to change that to kilojoules. So it's going to be 0.0345 kilojoules per mole Kelvin. All right, now guys, if we just plug this into our calculators and solve for the temperature, we see that the boiling point for the solution is going to be 681 Kelvin. Now, what's the significance of that? This is the temperature at which these two processes are at equilibrium. They're happening at exactly the same rate, and the position of equilibrium is like right in the middle. Neither one side of this process is favored. So let's just, we don't know what the solution is. Let's call it X liquid, okay, is going reversibly to X gas. At the boiling point, at 681 Kelvin, the position of equilibrium here is right in the middle. Whereas if we are at a higher temperature, if we raise the temperature of this solution, well then that's going to favor formation of the gas, and all the liquid is going to evaporate. If we lower the temperature, that favors the other side of the reaction. So it's going to go back the other direction. It's going to be non-spontaneous, well, you can say kind of, well, not non-spontaneous, but yeah, I guess it would be non-spontaneous. It's going to favor the reactant side, and so it's going to go back into the liquid at temperatures below the boiling point. So it'll be more liquid once equilibrium has been reached. But at the boiling point, guys, these two processes, condensation and boiling, or rather evaporation, are happening at the same process. So there you go. It's one application of this knowledge. Okay. Now we've been talking a little bit around equilibrium constants and equilibrium. So free energy for a process and the equilibrium constant are related. And there's two useful mathematical relationships you guys should take down about free energy and equilibrium. The first is extremely important. The change in free energy for a chemical process is equal to negative R times T times the natural log of K. Okay, times the natural log of the equilibrium constant. And the last one here is kind of less important, but you see here we have the degrees. So this is the standard free energy change. Okay, if we're looking at a process that's going on at 25 degrees Celsius. Well, if we're looking at something that is not at 25 degrees Celsius, okay, delta G at any other temperature is equal to the standard free energy change for the reaction. So if say we're looking at a process that's going on like at 500 Kelvin or something, right? That's equal to the standard free energy change, which is at 298 Kelvin, plus R times T times the natural log of Q, the reaction quotient. Okay, this is not really that major. You don't have to memorize this. Okay, one right there. But the top one, number one, is extremely and extraordinarily important. Okay, so what does it mean? If we have delta G is less than 0. Delta G is less than 0, that means it's going to have a negative sign, and that means that the reaction or the process is spontaneous. That means that K is greater than 1. The value of the equilibrium constant is going to be greater than 1. We can solve for that mathematically. Okay, and that means that the process is spontaneous. Okay, delta G is less than 1, or less than 0 if it's a negative. The process is spontaneous, and products. Okay, so the position of equilibrium is going to lie to the right. If you have the opposite case, where delta G is greater than 0, then the process is non-spontaneous. Okay, it does not have a tendency to happen by itself to a significant extent, and then that favors reactants. Now, if you consider the second case, if you have a non-spontaneous process, what that means for the reverse reaction, if we take it and turn it around, the reverse reaction then would be favored. It is spontaneous. Just kind of keep your mind. So if you have a non-spontaneous forward process, the reverse process is spontaneous. And we have this case here where delta G is equal to 0, and that means that the K value is equal to 1. And just like we were just saying here, neither is favored. Neither products or reactants are favored. So these are the meanings here and how we can apply delta G and K. All right, let's look at an example. So the utility of this is, if we know delta G, if we know the free energy change for a reaction, we can figure out at a particular temperature what is the value of the equilibrium constant. And also, if we know an equilibrium constant for a reaction, we can calculate the delta G value. So let's go through and do a couple of examples, and then that's going to be it. Okay, example number 1 of this sort of application. Okay, we're going to determine the value of K for the synthesis of ammonia. Okay, so ammonia here is going to be, the synthesis of ammonia looks just like this. So nitrogen plus 3H2, okay, goes in equilibrium with 2NH3. Okay, delta G for this process is negative 32.9 kilojoules per mole for the reaction. The question is the reaction spontaneous or non-spontaneous, and does the reaction favor reactants or products? Well, if we apply our equation here, delta G, okay, is equal to negative RT times the natural log of K. Let's solve this equation for K, guys. K, or actually, okay, let's go one step. Okay, the natural log of K, we get natural log of K by itself is going to be delta G divided by, or negative delta G divided by RT. Okay, if we get K by itself, K is going to be the natural, we have to undo that natural log. K is going to be E raised to the negative delta G divided by RT power. Let's kind of simplify this power here. Okay, we'll do this up here. Okay, delta G, like we just said, is negative 32.9 kilojoules per mole. If we change, negative of a negative, though, is a positive, so this is going to be 32.9 kilojoules per mole, okay, over R times T. Now, the value of R we're going to use, guys, is 8.314 over mole times Kelvin. But we have to have this, we want to change this to be the same unit as delta G. So we're going to make this kilojoules. So that's a change into 0.008314 kilojoules per mole Kelvin. Okay, so we'll put that down here. So we have 0.008314 kilojoules over mole times Kelvin times T, which is 298 Kelvin. If we simplify this, guys, this comes out to be 13.27. So there's going to be our power. If we take e to the negative 13, or to the positive, rather, 13.27 power, the value of the equilibrium constant K is going to be 6 times 10 to the fifth, or to the positive fifth power. And so the reaction, okay, we can say two things about this. First of all, the reaction is spontaneous. We know that because we didn't actually have to do any calculations to know that, because the original sign of delta G is negative. So we know it's spontaneous. And it favors products. We can see that clearly because K is way greater than 1. Okay, one more example, guys, and then that is going to, okay, we're going to calculate delta G for a reaction from a K value, okay? So we're going to consider this reaction right here. The decomposition of ammonium chloride, NH4Cl, is going to go to ammonia, NH3, plus HCl. Okay, these things are both gases. And ammonium chloride, guys, of course, you know, is going to be a solid. All right, now we're going to find delta G, because we know that Kp for the reaction is 1.1 times 10 to the negative 16th power. So let's plug that in here. So delta G for this reaction, okay, is going to be negative R times T times the natural log of K. Okay, now what's the temperature? Well, we know if this is a standard, right, standard free energy change, it's implied that the temperature is 298 Kelvin. Okay, so that's going to be the temperature here. So all we have to do, guys, is just plug this number into the equation. So R, again, is 8.314 joules over mole times Kelvin, and the T is 298 Kelvin, and then we're going to take the natural log of the equilibrium constant. If you plug that in, what you're going to get is 91 kilojoules per mole, and that is going to be positive. Okay, positive 91 kilojoules energy change. So, is the reaction spontaneous? Delta G is positive, guys, so you can say that, is the reaction spontaneous? The answer is no, it is not spontaneous. The reaction does not have a tendency to occur by itself to a significant degree, and we can also say that it favors reactants. We know both these things. We didn't actually have to do any calculations really to know this, because if you have an equilibrium constant which is less than 1, we know that that's going to lead to a non-spontaneous process that favors the reactants. All right, guys, that is the end of the podcast. Hopefully that was intelligible, and now go on and do the homework problems that are on the site, and I will see you guys all in class on Friday. Talk to you then.